Hey, time to do some physics from the book, chapter 1. This chapter is just about units and measurement. Can't really start doing math about the world until you can measure stuff, because we need some numbers. And, like the number 3, just by itself, doesn't really mean anything in the context of measurement. Physics. Got to have units. All right, so don't know why I picked 3 there. It's just a convenient number. So we're going to do 5, 7, 11, 15, 21, and 23. Let me write those down here. 5, 7, 11, 15, 21, and 23. So all odds, you tried these already, I presume, and checked your answers, just in case you're doing things out of order here. If you have not tried these problems yourself, then you are not supposed to be watching this video yet. All right, number 5. Horses are to race over a certain English meadow. Oh, that's nice. For a distance of 4 furlongs. Just going to write that down. And they want to know what's the race distance in rods and chains. So 1 furlong. Well, they have the conversions there, so I'm just going to refer to those. So what I think at this point, maybe you watched a little video about unit conversion that I made. But conversion factors are basically like little fractions that are equal to 1. So for example, when they give us these conversions, so you could say 1 furlong is equal to 201.168 meters. That's a fraction that's equal to 1, because these two things are the same, and which means I can write it upside down. It's still equal to 1. And also 1 rod is equal to 5.0292 meters, and 1 chain is equal to about 20 meters. So each one of these you can think of as like a fraction that's equal to 1. And of course you can multiply anything by 1 and leave it intact. So we would like to know what 4 furlongs is in part A. We want to convert that to rods. So I'll start with 4 furlongs. I'm just going to abbreviate these, and I can put that over 1 if you like. That's the thing we're trying to convert. And I'd like to get it to rods. So let's see. I know that if I go to meters first, then I can get from meters to rods. So the first thing I want to do is get to meters. So looking at my conversion factor, I need this, but I need it upside down, because I would like the furlong to cancel out. So 201.168 meters. And then I would like, now I've got meters, to get from meters to rods, so I need the meters to be down here, so they cancel out, and 5.0292, oops, sorry, that's probably a pretty easy mistake to make. It's 1 rod is equal to 5.0292 meters. So be careful there. Don't make that mistake like I did. And then you multiply that through, and you get the answer, which is, let's see, 160 rods. Now, probably your calculator gave you a lot more digits than this. So why would you round to just 2? Well, the thing that we were converting just had 2. So no matter how detailed, no matter how many significant digits we have in the conversion factors, we really have no business reporting more than this, right? Than this many. I'm not going to fuss at you too much. I'm just going to stick with the the College Board guidance that you should report answers with a reasonable number of significant digits. And that means between 2 and 4 to them. So I'm not going to fuss too much, but the rule here is that we should not be reporting more than this. It should be the same number, 2 sig figs. Part B, we want to turn that into chains. So I just have to add one more conversion factor there and multiply through. I'm not going to write that all out again. And after you do that, you should get that that's about 40 chains. All right. And actually, to turn it into chains, we're not going to, sorry, I said we would add one more. We would replace this conversion factor with this one, is how we would do that. So you can try that and see how you do with it. If you really wanted to fuss about significant digits, then really you could do that, because this number really only has one significant digit, the 4 there, so that is a 0 without a decimal there. So you could do that too. That's fine. All right, number 7. Hydraulic engineers in the United States are often use an acre-foot, defined as the volume of water that will cover 1 acre of land to a depth of 1 foot. My house is on an acre, just about. It's about 1.059 acres. So I could imagine my yard with 1 foot of water. I can definitely imagine what an acre-foot is. Severe thunderstorm dumped 2 inches of rain in 30 minutes on a town of area 26 square kilometers. What's the volume of water in acre-feet that fell on the town? Okay, so we got to figure out what we have here at first. So we don't have acre-feet. We have like square kilometers times inches. So that's, in terms of dimensional analysis, that's the same dimensions, right? An acre-foot is like an acre is this, that's an acre, and then a foot high. Of course, that is not to scale. So that's kind of like what an acre-foot looks. So you could think of an acre-foot as being like an area times a height. Of course, it's just a 3-dimensional measurement, but an area times a height. So what I have here, I have my square kilometers, 26 kilometers squared. I need to convert that to acres, and then I have the height of it is here 2 inches. I need to convert that to feet, and then I need to multiply those two things together so I can get acre feet. Right now I have square kilometer inches. So let's see what we can do there. Square kilometer, I would like to get that to, what if we went to square meters first? So 1 square kilometer, well, 1 kilometer is 1,000 meters. But if we're dealing with square units, we have to square these, and we have to square any numbers that show up here. We have to square those conversion factors also. So that'll get me to square meters. And then I happen to know, this is a good one, I think, that, well, let's see. At some point I might need to look something up, because, let me think if I know. I think at one point I knew how many square feet there are in an acre. It's, I think, something like 43,000, oh boy, 460? It's something like that. Okay, I'm going to flip to the back of the book. In case you didn't know this, in the back of your physics book, where is this? Let's see. On the very back cover, there's some things, but maybe not what we need. It doesn't have area. There's another maybe Appendix D. Yes. This is on page, it starts on A5 in the back of your book. So for area, this is on the bottom of page 5 in your textbook. We have 1 acre. It's 43,560 feet. Right? So I'm going to use that, or I'm going to try to use that and see how it goes. You probably could look something up and do it in less steps than what I'm going to do, but this is one that, well, I almost remembered. So let's see. I've got square meters now. So I do know that. Let's see. Let's get to miles. So I know that there's 1,609 meters in 1 mile. So this is square meters. So I'm going to have to square these. And that's got me to square miles now. And I also know that there are 5,280 feet in a mile. But we're talking square miles here, so I need to square those. And then I know here that there's 43,560 square feet and an acre. And I don't have to square these because that is square feet. It's already there. All right, so let's see. Multiply this chain of things together. I don't know if you can see the screen there, but you know how to use a calculator, so I'm sure you're fine. So 26 times 1,000 squared divided by 1,609 squared multiplied by 5,280 squared divided by 43,560. And that gives me, I'm going to say that that's, are we off the page there? No, you can see that. So about 6,430 acres. And now, this is going to be a lot easier, this one. I know that there's 12 inches in 1 foot. So that's 1/6 of a foot. Or if you want, 0.17 feet. So if I take this number here, divided by 6, I get about 1,070 acre feet. And let's check that. The book rounded that. They did 2 significant figures, so they called this 1,100 acre feet. And I included 3 digits. They are more correct than me because that has 2 significant digits, so I probably should have done the same thing. But this is, I'm okay with that answer. That's a little bit more paying attention to significant digits. All right, that is not the only way to do this, but I think that's how I would advertise doing it. Number 11. Let's see what we got here. For about 10 years, okay, I love this. I really love this question. So, for about 10 years after the French Revolution, the French government attempted to base measures of time on multiples of 10, in other words, metric time. 1 week consisted of 10 days. And 1 day consisted of 10 hours, and 1 hour is 100 minutes, and each minute is 100 seconds. So what are the ratios of the French decimal week to the standard week and the French decimal second to the standard second? So the thing, it's not, I shouldn't say the trick. The issue here is trying to understand, like, where is the equivalence, like what is equal to what. So like a second here isn't this going to be the same. One of these metric seconds isn't going to be the same. Minute's not the same. An hour is not the same. What is the thing that is the same? A day is the same, because the sun comes up, the sun goes down, then the sun comes up again. That's a day. So the thing that is immutable here, the thing that the French are carving up here, or that the rest of us have decided to carve up, is the same thing. It's a day. So the week, for part A, since we're talking about the same, the days being the same, if one of these metric weeks has 10 days, then the ratio of the French decimal week, French week to, let's say, normal week is 10 to 7. Because theirs is 10 days long, ours is 7 days long, and that's the same, the days are the same. The sun goes up, the sun goes down, and then it comes up again. So the things that we're comparing here are the same, those days. Now the seconds, on the other hand, those are not the same. So let's see. How many seconds are there? The thing that is the same, so let's see, we want to know a French second to a normal second. We would like that ratio. So let's see, how many normal seconds are there in a day? I happen to know that's, let's see, there's 60 seconds in an hour, and 60 seconds in a minute, 60 minutes in an hour, and 24 hours in a day. And I happen to know, because I teach physics and it comes up, and I remember things sometimes, that there's 86,400 seconds. I should write this more neatly as a proper conversion factor in one, I'm going to say ND, normal day. Right? Now what about this crazy metric time? Well, let's see. I have 100 times 100 times 10 times 10. 1, 2, 3, 4, 5, 6 zeros there. So, oh, wait a minute. Oh, no, I don't need to convert to the week. So just 1, 2, 3, 4, 5 to get to a day. So it's pretty close. There's 100,000 of these seconds in a one, let's say, FD for French day. Okay, so how do we figure out what this ratio is? Well, the days are actually the same, right? So those can cancel out. So let's see. If I have French second, I have 100,000 of those is one day. And then normal second, if I want that, this is normal seconds. If I want those to cancel out, then I have 86,400 normal seconds over one day. So the days cancel out, and I get a pure ratio of 86,400 over 100,000. So 0.864 would be that ratio. If you had that number upside down, if you had something that's a little bigger than 1, that's an easy mistake to make. We could just think about, like, why is this the ratio of the French second to the normal second? If there's 100,000 of those French seconds, does that mean that they're longer? So this would be bigger than 1, or they're shorter. This would mean that they're shorter by a little bit, right? Now if you think about that for a minute, if you have a day, right, here's a day, and you're going to chop it up into a bunch of pieces. If you chop it up into more pieces, like 100,000 versus 86,400, then the pieces are going to be a little bit smaller. So those French seconds are smaller because you have taken the same day and cut it into more pieces. There's, I don't know if you guys know who Yogi Berra was. He's a famous baseball manager guy. And he was famous for saying things that were sort of absurd but somehow very deep at the same time. Like, for example, he said once, when you get to the fork in the road, take it, which is kind of a silly thing to say. And he, in the context of this problem about our dividing the day up into lots of pieces, he allegedly went into a pizza place once and ordered a pizza, and the person at the counter said, Mr. Barrow, would you like us to cut your pizza into 6 slices or into 8 slices? And he said, you better make it 6 because I'm not that hungry. Think about that. Okay, so number 15 is where we are at. A fortnight is a charming English measure of time equal to 2 weeks. It says 14 nights, fortnight. It's also some other thing, I guess, that you guys know about Fortnite with dancing or something. I don't really know about stuff like that. So that's a nice amount of time in pleasant company, but perhaps painful string of microseconds in unpleasant company. How many microseconds are in a fortnight? Okay, so basically we're just doing one fortnight. And that is 14 days. You could go 2 weeks and then to days, but you know we can skip that step, I think. And we want to go to microseconds. All right. So how many? We just did this. So come on. You remember, right? 86,400 seconds in a day, and then I want to go from seconds to microseconds. That's the abbreviation for micro, and micro is 10 to the negative 6, right? So back to that little unit conversion video that I made. You may have different ways of doing this. This is how I like to do it. So as long as you're doing something that works. Multiply all that through. Let's see. We got 14 times 86,400 divided by 10 to the negative 6. Be careful here. Don't do 10 negative 6. That means 10 times 10 to the negative 6. When you hit that little thing, that's going to take whatever number you put here and multiply it times 10 to the whatever power. So that is different than 10 negative 6. So this says that we have, let's see, how many, they said 2.0 weeks. They had 2 sig figs, so I will follow suit. All right, so 1.2 trillion microseconds. Let me just check that with the answers here, make sure I didn't do anything wrong. They said 1.21. They kept one more significant digit. I wonder why they did that. I'm totally fine with this answer, though. So 1.2, 1.21, something like that. That was easy. All right. Am I doing 17? No. Next one is 21. All right. So mass now. The Earth has a mass of, so mass of the Earth is, what is it? I've seen different numbers. Sometimes you see 5.97 here, times 10 to the 24 kilograms. Average mass of the atoms that make up the Earth is 40 U. And what does that mean? What does that little U mean? That's atomic mass units. So I want to convert. Let's see, what do we want to do? How many atoms are there in the Earth? So I need to convert this to atoms. And the average mass of those atoms is 40 U. So that's a conversion factor that we're being given there. That means one atom on the average is equal to 40 U. So that's a conversion. I can make this a fraction with either one of these top on top and the other on the bottom. All right, so let's start the chain going. 4.98 times 10 to the 24 kilograms. And then I want to get from kilograms to atomic mass units. So let me just make sure. I got to guess at what that is, but that's not a number that I roll out of my brain too often. So I'm going to make sure. Let's see, mass. One atomic mass unit is 1.661 times 10 to the negative 24. I think that's grams. And 1.66 times 10 to the negative 27 kilograms. I think I might have remembered that. All right, so let's see. Let's go from, I think I'm just going to do it in one shot. So 1.66 times 10 to the negative 27 kilograms. If I were to remember it, that would be the number that I'm going to remember. So here, I've got 1.66 times 10 to the negative 27 kilograms, putting that on the bottom because I would like those to cancel out. That's equal to 1 atomic unit, mass unit, and here 40 atomic mass units on the average. That's like one average atom. And that's it. So I've got 5.98 times 10 to the 24 divided by 1.67 times 10 to the negative 27 divided by 40. That gives us about 8.95 times 10 to the 49 atoms. And we'll check that against the book answers to make sure we didn't make any mistakes. And they did 9.0 instead of 8.95. That's fine. All right. Do you know how many atoms there are? How many atoms that we estimate there are in the universe? We think that there's about 10 to the 80th atoms in our I think this is you have to ask a cosmologist, but I think that this is in the observable universe. Is what we say about that. So there you go. So it's easy to get fooled by scientific notation and go, wait a minute, look, we have, like, in the Earth, there's 10 to the 49 of them. Isn't that like more than half of that? And of course, that's not hardly true. You'd have to multiply this by 10, 31 times to get to this. Or actually, I guess maybe 30 times, since this is almost at 10 itself. But you know what I mean. So that means that the Earth, how many Earths would you need to make up the entire universe? If the entire universe were only made up of planet Earths, how many of them would you need? Well, if this is about 10 to the 50th, then you'd need 10 to the 30th of those Earths, which is, let's see, 1,000,000 trillion trillion trillion. If you want to just stick to illions that we use usually, 1,000,000 is a 10 to the 6, and trillion is 10 to the 12. So if I had, that adds up to 30, right? 6, 12, oh no, just kidding. That's bad math. I just need 2 of those, 24 and then a 6, right? So that'd be 1,000,000 trillion trillion Earths. 1,000,000 trillion trillion Earths is how many Earths you could make if you took all of the atoms in the universe and just made Earths out of them. You could make 1,000,000 trillion trillion of them. That's fun to think about, I think. Let's see. Last one. 25? No, 23, just kidding. 23, what do we have here? Assuming that water has a density of exactly 1 gram per cubic centimeter, find the mass of 1 cubic meter of water in kilograms. All right. So let's just go ahead and do that part A first. We want to find the mass of 1 cubic meter of water in kilograms. Okay, so I have 1 cubic meter of water, and I want to convert that to kilograms. So first of all, I need to get to centimeters, cubic centimeters. So in 1 meter, there are 100 centimeters. I actually like to do it to be consistent with, if I put a centimeter there, sorry for being messy there, centimeter means 10 to the negative 2. So 10 to the negative 2 meters is the same as centimeter, because that's what the centi means. So just like those cancel out, these mean the same thing and cancel out. Now, of course, I'm doing cubic units, so I have to cube both of those. Okay. And then that gets me to cubic centimeters, and I know that 1 cubic centimeter is 1 gram. I don't have to cube this, because that is the conversion factor, and they're both ones anyway. And then grams to kilograms. Kilo means 10 to the third, so where that K shows up on the top, I put the 10 to the third on the bottom. And then if I rattle through that conversion, I should get that there are 1,000 kilograms. That's a metric ton, folks. In a cubic meter of water. All right. Part B. What is the mass? Oh, sorry, backing up. Suppose that it takes 10 hours to drain a container of 5,700 cubic meters of water. What is the mass flow rate in kilograms per second of water from the container? Well, it's the mass flow rate is, let's see, 57. Let's first convert 5,700 kilograms to, oh, wait, hold on a second. Did they say, no, they said cubic meters, not kilograms. So let's convert that to kilograms. So 1 cubic meter of water is 1,000 kilograms. And are they going to want it in, yeah, they want kilograms per second, so kilograms is good. So that's 5.7 times 10 to the 6 kilograms of water. And now that's going to take how many seconds? Well, let's see, it takes 10 hours. So 1 hour is 3,600 seconds. So that's 36,000, or 3.6 times 10 to the 4th seconds. And if you want the mass flow rate in kilograms per second, well, I've got this many kilograms in this many seconds. So 5.7 times 10 to the 6 divided by 3.6 times 10 to the 4. And that should give me, oh, I don't know, 1 and change times 10 to the 2, looks like. Yep. So about 158 kilograms per second. That is the mass flow rate. All right, there's that assignment done. Hope that was helpful, and see you later.